So let's remember about rotational energy. Angular velocity, or omega, is the number of rotations that are done in a period of time. So it is the same as, it's like velocity, where it's distance over amount of time, but here it's the angle or the rotations or just the angle theta that is completed over time. So angular velocity omega is going to be a much higher if you travel a larger angle or you travel an angle in a smaller amount of time. So it is like velocity, but it happens in a circular manner. And I'd like you to remember, please, that if we draw a circle of radius r, then the tangential velocity, let's say it's rotating this way, then the tangential velocity v is the velocity at the tangent from that circle and at radius r. So that's where we have that famous formula v equals omega r. So I just want you to remember that equation. I also want to bring your attention to something that's very common, and that's the units you use in these rotational types of situations. Revolutions per minute is very common, and radians per minute is also very common. And I just point you back to the circle where an entire revolution has 2 pi radians in it, so 6 and a bit radians. And just knowing that, and also knowing that there's 60 seconds in a minute, it's easy to convert between the two. And that's where we often see 2 pi over 60 in formulas, or pi by 30. And I believe our 9.55 that's in some motor equations are actually that, because of this 2 pi over 60 relationship. So please remember that as well. So in this course, we're going to get into some generators, which of course are rotational energy devices. So I need you to remember this formula: synchronous speed of motors, 120 times the frequency divided by the number of poles. So here's just an example for you of a 2-pole motor with a frequency of 60 hertz. Find the speed and do it in radians per second to give you some practice going from RPM to radians per second. So it's a pretty straightforward exercise to substitute in the frequency and the number of poles into this equation, and then we remember that RPM is actually a revolution per minute, and then we can figure out, we can remember how many radians, there's 2 pi radians in each of those revolutions, so we cross out the revolution, and there's 60 seconds in each minute, so we can do that conversion. Angular acceleration, remember that we had displacement, and then we have velocity is displacement over time. Then we had acceleration is velocity over time, or acceleration is displacement over time and over time again, so over time squared. And now we have the same thing in rotation, where we have displacement is theta and angle, and then omega is the change in theta in the angle over time, and acceleration, angular acceleration, is the change in angular velocity over time. And I just want to remind you that if we break out this change in angular velocity, we call that angular velocity 1 minus the initial velocity, then we can prove this equation is true. And then through further substitution, which I'm not going to do here, a formal proof, but we can prove this equation as well. So I'm giving you here the relationships between angular velocity and angular acceleration and position in these handy formulas, which are akin to their linear counterparts that we have previously studied. Here's an example of where we would use that. This one is a flywheel, but you can easily extend this knowledge to, say, a wind turbine that is spinning, but it has to be slowed down because it has been taken off the grid. So this flywheel is slowed down from 2000 RPM down to 1800 RPM, and that is in 10 seconds. So here we can calculate the deceleration of that flywheel. And it's a matter of substituting into this equation that we had from above and being careful of our units, because we were given units in RPM, but this equation works in radians per second. So that is shown here, that the initial velocity is in radians per second if you're going to use this relationship. You'd have to draw out the proof to illustrate why that's in radians per second, but in this question we did have to convert to radians per second before we substituted them in. Of course, the answer is in radians per second squared, because the an acceleration or a deceleration in this case is the second derivative of the position, the angular position.